Okay, so we're going to go over section 2.6, polynomial and rational inequalities. A lot of this stuff we already know, what we're going to use we already know. We worked on them with the graphing polynomials and the rational functions. But we're just going to do this inequality part and figure out how to do our solutions. When we have equalities, we only usually have certain points that make the equality work. With inequalities, we'll have a whole set of solutions. So we're going to have to write intervals for these solutions. And I'll show you what those are. Okay. So first off, we're going to start with the polynomial part. Basically, this is an overview of what we're going to do. We're going to, if we've got an inequality where we've got two parts of it, we're going to get everything over on one side. And then instead of comparing something to like a 15 is f of x greater than 15, we're going to look for like f of x being greater than or equal to 0, less than 0, greater than 0. That is basically the set. So when these things, now what we do is just look at things like the graph. When is the function positive? So above the x-axis, this is all the greater than 0. If I include this, that would be greater than or equal to 0. If I'm talking about, let's say here, if I draw something here, this would be this area over here and here less than 0. All of these are negative signs. And if I include these points along with that, I would be saying less than or equal to 0. So that's how we're going to do, and we'll just be able to read off the intervals. If we have it graphed, that's pretty easy. I would just use these points, this points, and write these intervals. Up here, I would just say if I'm looking for f of x greater than 0, I just use these points, don't include it. Let's say if this was A, this was B, I would have my open interval. And then if I had greater than or equal to 0, I would have include these points. Excuse me. Okay, so that's kind of what we're just going to do. If we've got the graph, we're just going to read it off from the graph. If we don't, we're going to use a little technique, and we'll build on that technique as we go. Okay. So there are certain points on the interval. Okay, so here, the zeros, this is where we can change sign between negatives and positives. 0 points. There are also another point that we have to worry about when we do rational functions that we have seen where if we have a vertical asymptote, that it's possible for this thing to change signs. I could go positive to negative, the graph is negative, across that, let's say x is equal to a, across a vertical asymptote. Not necessary, I could go on the other side, come down here and have a plus, but in that picture, I've actually changed signs. They call them boundary points. Okay, the boundary points would be vertical asymptotes and zeros. I've always called them critical points. Critical points. Where the signs could change. The sign of the function can change. Okay, they call them boundary, that's fine. But what we're going to do is try to find these boundary points. We know how to do that. The zeros of the functions, where the denominator is equal to 0, where we do our vertical asymptotes, and then do just some test points across here. We could graph it, read it off the graph, or just do some test points and build a table. I'll show you kind of how to do that. Okay, so here is this graph. Okay, it says solve, so I'm not going to talk about the graph. This is not the graph of that naturally. But what we're going to do is if I've got an inequality like this, I want to know what x's, what are the x's the interval, right? The interval where x, those x's times x minus 2 would be less than or equal to 15. Okay. So what I want to do is turn this thing in and always compare it to 0. Okay. So I want to get this. I like to keep my x's positive. So I'm going to get everything over there. I'm going to expand this. So I'm going to go, distribute x squared minus 2x less than or equal to 15. And then I'm going to move this over here. So I'm going to subtract 15 from both sides. Okay, so I get x squared minus 2x minus 15 less than or equal to 0. Just like we did when we're solving this, we're always doing a quadratic, comparing it to 0. Then we can get factors in here, do the 0 property. And then we're just going to look like, okay, well, we want to know the zeros because we're including them, but where is this product negative, or where is all of this negative? Okay. So naturally, the same thing that we've always been doing, factor, quadratic formula, find a 0, and then go through synthetic division to finish out the factoring. Okay, so here, this one we can factor. I'm looking for 2 factors of 15, where the difference, because of that negative sign, would be negative 2, would be 2. And I think 3 and 5 would work. So the largest is going to be the negative sign, and those 2 factors would be 5. Have to be a different sign because that's a negative. X squared plus 3x minus 5x minus 15. The plus 3 minus 5 gives us the negative 2. Okay, so I want to test when this is less than or equal to 0. My 2 zeros, I'm going to include x minus 5 is equal to 0, so x is equal to 5. X plus 3 is equal to 0 at x equal to negative 3. So we're going to include these endpoints. So if I draw like a quick line here, I can do this just with this. So here's negative 3, left to right number line. Okay, put a 0 here. I don't need that point though. Here's 5. I know this thing touches here, so it's either going to be here or here, and go through those zeros as a quadratic. All I need to do is pick some point in here to tell you what it is. We know what it's going to be though. This is opened up, the graph. This is this over here, but I'm not going to look at the graph right now. I'm going to say, I know this is opened up because of the positive coefficient here. So this has got to be like that. Okay, so the intervals, this is positive. F of x is greater than 0 over here, less than 0 here, and positive there. If I don't like doing this, then I do a test point. 0 is always good as a test point. Large numbers out here. 0, if you can get it in here. 0 would be 0, 0. This one would be 0. That would be 0. Negative 15, which is certainly there, negative. And then I'm asking, what do you want me to, what interval? Do you want it positive or negatives? And it's the less than or equal to 0. So my solution set looks like negative 3, 5. These included to make any number in here is a negative number for the function, and these are included for the equals. And now if I go over here, if I was given the graph of the function, I would read it off just from the intervals. Negative 3 included all the way up to 5. Now this graph is the graph of this. This doesn't have a graph. This is just asking for something. This is just an inequality. This, going through this process, develops a graph, and then we can look when we compare it to 0. Okay, so let's look at another one. This one if we set this equal to f of x, everything is already over on one side. So this is the function that we would graph. I've got the 0 here's 2. There's the 2. Multiplicity 2, so it just touches. X equal to -3 is the other. So I am basically going through a polynomial graph if I got that. So I have f of x, x minus 2 squared, x plus 3, and I graph that. This is a 2x squared times x cubed. So this, if we expanded this out, is a third degree poly. Third degrees, any odd degrees are up, from down, up. Okay, so if we looked over here, that's what that's going to do. That's what that's going to do. My 2 zeros are the x equal to 2, multiplicity is 2, and then our x is equal to -3. I've got to start from here, down, and I've got to end up from our third degree poly. The only other thing I need, this was my 2 with multiplicity 2, multiplicity 1, so that goes straight through. This is going to be a touch or a touch. Only other thing I need is the y-intercept, f of 0. That's just -2 squared from that x being 0. This x is 0, so we're just multiplying that times 3. -2 squared is plus 4 times 3, so this is just 12. So up here at 12 is where this is going to be. So a quick graph would be here, up, just touch, and then that ends up like we're expecting. We're starting here and then ending up there. That gives us a quick graph that we could do. And then what are we asking? Is when this thing is less than 0. When this stuff is less than 0. So that says when that function is less than 0. That means this interval from here to here, and then this doesn't include. Strictly less would be the interval from -infinity, because I'm starting way out here, -infinity, going up to -3, and then I do not include that. If I said less than or equal to 0, I would include this point, and then I would also have to do that 1.2, because that would be equal to 0. If I'm given the graph, again, all I have to do is just read this off from the graph, okay? So this would be more in tune to saying, okay, where is f of x less than 0 when f of x is equal to x minus 2 squared, x plus 3, like that, okay? So you would graph it and then just read off what you're looking for. Less than 0 being negative numbers, greater than 0 being positive, and then do you include the x-intercepts if this is equal to 0? And you do. Okay, so let me redo this. Instead of doing it graphically, let me show you another method that works well when it gets very complicated. The graphing gets complicated. This tends to be a little easier, and this is called a sign chart or sign table. And what I want to do is basically examine each one of the factors. I still have to have everything in the factors, but what I'm going to do, I have to do the very same thing, identify the critical points. We did that 2 and -3. So I'm going to set up different intervals like this was a number line. So let me kind of rewrite this as a -3, 2, and then I'm going to write those with the points on a number line, and I want to use that, okay? So I'm going to start an interval, -infinity up to -3. This would be including -3, and then the interval -3 to 2, and then 2 out to infinity. So this is like if I put a little number line here, -infinity out to infinity, and I just do these intervals between these points, okay? That's what I've done here. And now on this side, what I want to do is take a look at each one of these. Now I could write x minus 2. I could go ahead and just put squared there, okay? And then x plus 3. So each one of the factors, if it's a rational number, I continue down from the bottom, everything in the numerator and the denominator. Okay, so what I'm going to do is kind of put some lines here. And I'm going to evaluate what each one of these factors are in this interval, okay? So this is easy because I've got the squared. If I picked out negative 1,000, something in here, a test point, this is still going to be positive. Even though this number is negative, I squared it. So all across, that one's going to be positive. It doesn't matter, 0, negative 2 squared is going to be positive. And then something big, 1,000, that's as positive numbers, and it's still going to be squared. So the squared let me go ahead and do that without even thinking about it. But this, I've got to think. Negative 1,000 plus 3, that's just going to be a negative sign. All I need to know is not the numbers, is just the sign of this factor and that interval. And the only way it's going to change signs is if I go across one of these points. Okay? So here, let's pick out a 0. 0 plus 3, now I've gone to a positive. It happened right there at that negative 3, right? So I switched over, and now 2 to infinity plus 1,000, that's going to be positive. Now what I'm doing with these signs is now I'm multiplying this. I don't really care about the number. I just want to know if it's above 0 or below 0. So I'm multiplying all of this together just like here, and this is my result, okay? Positive times a negative is a negative. Positive times a positive is a positive. Positive times a positive is a positive. I've got all of the signs, and if we look over, if we compare that to the graph, let me kind of get over here. If we look, here's the negative, here's the positive, and then there's the positive on the other side, okay? And then I'm just asking, once I build this, it tells me everything. So if I want to know when f of x is less than 0, the negative sign, it is just that interval. I don't include the endpoint because that's not. If I want to know when f of x is greater than 0, this is the ones I'm going to use, okay? Now, here I have to be careful. If I wanted to know strictly greater than 0, I would not include this endpoint. So I would look at something like negative 3 to 2, union 2 to infinity, because I'm not including it. And if I wanted f of x greater than or equal to 0, I would do the negative 3, that 1 point. So I would say like negative 3, union, and then everything else. There and there. So that would actually include it because it doesn't go negative, okay? So I go from negative 3 all the way out to infinity. Here, once I hit here, there's 0, and I can kind of continue it out. If I just touched, I would just want that 1 point, okay? But this one gives me everything here. So I read that off. I say, what am I looking for? And just go to the intervals above. This works better once I start doing, if I got a quick rational or something, I do the very same thing, and I don't have to do all of the graphing to read it off the graph. So I'll do this again. It's a really good way to do this. Let me continue on. We'll do a couple more of these. Let's do this one. Okay. So I've got 4x squared minus 20x plus 25 less than or equal to 0. And here I've got something in here with a 0. So if I graph this out, it would be in here like 2.5. Looks like it's going to be in here. So let's kind of work this through based on completing the square. Let's do it that way. Okay. So I want to complete the square. I want to set this basically equal to a function. Okay. That's what I want to do here. And then evaluate the function. I can complete the square. This looks like I can factor out a 4 pretty well. So I'm going to go 4x squared, divide that by 4 minus 5x plus 25. And for the moment, I'm just going to say that's kind of like a function that I want to read off. I want to put this in vertex form. Okay. So half of this would be 5/2 squared would be 25 over 4. Okay, so I've really added in a 25, so I need to subtract off a 25. So this is actually x minus 5/2 squared minus 25 plus 25, and this is equal to 0. Okay. So I want to know if this was graphed out, when is that less than or equal to 0? And this is when it's equal to 0. This is always positive. This is always a positive number. This is positive. When I square it, this is always positive. So the only thing I'm looking for now is less than 0. The only point is where this is equal to 0. This is always positive. So at x, if I solve this, x is equal to 5/2. Multiplicity is 2. So if I graph this thing, there's where we are, and it just touches. So the only point that satisfies this thing is x equal to, so here is my interval here. This is just 1.5/2. Okay. So if I wanted to know, this is the same thing, but now I'm asking, where is it greater than or equal to 0? So we've already got all of this set up. We know what this looks like. This is just, if I'm looking at this as a function, this is f of x, ax squared. There's my 4. So it is this function shifted to the right 5/2 units, or 2.5. Okay. So now they're just asking, where is this greater than or equal to 0? Same function, they're just asking this question. And this is always positive, equal to 0 at 5/2, negative infinity to infinity. Let me go in for this. Let's start these. We'll go back and work some of those. But I want to kind of introduce these with rationals, inequalities. It's the same principle. Anytime I have a rational, and if I'm comparing to the two things like, 2 over x plus 3 less than or equal to 5x. Once I see this, I want to get everything over and compare it to 0. So I would have to combine that up and then factor. Okay, but this has already been done for, so here's the basics. So I've got x minus 1, x plus 3, x minus 4. To do this as a graph, I've got to realize that this is a degree 2, degree 1. What would the things that I need? Vertical asymptotes. Before I even worry about vertical asymptotes, I want to make sure that this degree of the top is less than the degree of the bottom. Yes, that's the vertical asymptotes is still going to be where the denominator bottom equal to 0. X minus 4 is equal to 0 there. That's a vertical asymptote. It's going to blow up if we see here. But look at this thing, it kind of goes up. That's where we're going to have to evaluate when we get to a horizontal asymptotes. We're going to say the degree of the top is 1 more. This is an x squared. The bottom is 1. So we would have to divide it out. Okay. We'd have to go through that process, get the graphing going, and do that. I want to do this with the sign chart. Okay. We'll graph this out. We'll redo this and graph it out in lab. But I want to do this with a sign chart. Okay, I want to re-emphasize this. How do I do that? So the places that this thing can change sign is here, here, and across that vertical asymptote. Doesn't have to, but that's where it's going to. A linear function, I'm going to change sign, change sign, change sign because of that vertical asymptote. Okay. So I want to set each one of these equal to 0 to find the boundary points or critical, okay? These are the critical points for me. Critical, and they could change sign. So I set each factor equal to 0. X minus 1 equal to 0. So I've got x equal to 1. And then x plus 3 is equal to 0. -3, -3, so x is equal to -3. These are the critical points. Now, what I'm going to do is do a quick little number line. I'm going to merge this into my table. And you're going to see what I would do. It's just going to save a few seconds. Okay. So starting left to right, which numbers left to right? That one comes first. So I'm going to put a little -3, and then somewhere 1, doesn't have to be to scale, and then somewhere out here at 4. Okay, that's my number line. This automatically sets my intervals up. So this is -infinity to -3, -3 to 1, and then 1 to 4. And then 4 to infinity. Those are the intervals based on where this thing is going to be. There's not going to be a sign change anywhere except when I go across these points. Okay, so what I want to do now is extend this down. Open this up a little bit. And I'm going to write each one of these factors. Doesn't matter which one I start with. X plus 3, x minus 4. Okay, so I kind of extend these down, these breakpoints. We'll go here. And now here's my result. This is where I'm going to read which interval is where I'm worried about. Okay, so I look at this interval and I do a test point in here because I'm looking for the sign. Something bigger this way of a negative, between -infinity and -3. Pick a large one so that there's no doubt. -1000 is in this interval. -1000, the sign is negative. -1000, that sign is negative. -1000, that sign is negative. We'll do this at the very end, but let's go here. This is a very narrow, but I can pick out 0 in here. I want to do 0. 0 minus 1, negative. 0 plus 3, positive. 0 minus 4, that's still negative. Now I got to pick out something in here. Let's do 2. 2 minus 1, that's positive. 2 plus 3 is positive. 2 minus 4 is negative. Okay, so this one changed sign. Now pick out something large, plus 1000, positive, positive, plus 1000, that would be positive. And now I get my results. Odd negatives 3 of them, that's going to leave a negative sign. Negative times a negative is a positive, and then that guy gives me a negative. 2 negatives, that would be a positive and a positive. Now I've got an odd -1, so that's going to be a negative, and then everything positive. Once I have this, I've got all the answers to whatever you want to ask me about this. Okay, that's why I like doing this. Now just fire away at the answers. Less than or equal to 0, this one. This one. And the only thing I need to do is refresh. Where's this thing equal to 0? I can't include the 4 because that's a vertical asymptote. I never can have the 4. But the 1 and the 3 I do. So -3, that's a 0, so I include that. Union sign, and I include the 1. So that gives me all of the things that I want greater than or equal to 0, here to here, here to here, and I include the zeros, but never a vertical asymptote. Okay, so again, the reason we like to do this is because we can go through all of the different variations of here. Where's this equal to 0? X equal to 1, x equal to -3. Where is it strictly positive? Over this interval, because here's the results positive, and this interval. When I get the include the zeros, I never include the vertical asymptote, so that's always got to be open, but I can include the zeros if I've got the equal to 0 as well. Okay. So we'll take a do a few more. What happens for this case though? Okay. If I am comparing my inequality directly to another number, okay, let me slide this over. So here I'm doing a rational, got a rational here, and I want to know less than 3. I always want to compare to 0. That's required, okay? So how do I compare this to 0? Well, I subtract 3 from both sides. I make this 0, so I subtract 3 from both sides, and then we'll handle it from there. X minus 5, x minus 7, minus 3, less than 0, okay? I have to combine this, okay? Just like I did the polynomial, the quadratic, get everything, I do the very same thing. And how do I do this? This is really 3 over 1. I need that to be over that. Same denominator, then I can do and see if I can factor or come up with something. Okay. So this, I need to multiply times x minus 7 divided by x minus 7. So I'm only multiplying times 1. This over this is 1, but this will give it to me. So x minus 5 minus 3 times x is minus 3x. Minus 3 times -7 is plus 21, right? Okay. And then all of this now is over x minus 7. And I'm just asking when that is less than 0. Combine, so this is now -2x plus 16. So I can do this a couple of different ways and it's not going to matter. But if I have it in this form, it's going to be easier for me to evaluate. I can factor out that -2 from here and here. 16 is divisible by 2. So I'm just going to rewrite this for a second as -2x minus 8. I've divided by -2. So there's my results. And then x minus 7. And I'm looking when this is less than 0. Okay. Now I'm going to do a sign chart. What are my critical values? x minus 8 is equal to 0 at x is equal to 8. X minus 7 equal to 0 at x equal to 7. Okay, so my chart looks like this is very close together, but out here at 7 and then at 8, infinity, negative infinity. Okay, so let me kind of rewrite this stuff. Let me reuse my board so that I can get a table in here. I don't need that anymore. I want to build my table. I'm going to use this up here. So I've got from negative infinity up to 7. And then I've got 7 to 8. That's my second interval. And then 8 to infinity. Those are my intervals. Here are my different factors. And here I have to remember this negative 2. That negative 2 flips everything. That's going to flip the signs all the way across. It's always negative, never changes sign, but that negative needs to be in there for my result. And then I've just got the 2 factors, my x minus 8. I write it like that as a factor. And then x minus 7 as a factor. Okay. And now I just do some evaluations. This needs to go across like that. And now I just need to pick some numbers. Large numbers. Negative 1,000, that's going to be a negative. Negative 1,000, that's going to be negative. Negative 1,000 is in this one. This one is very small. All I can do is pick like 7.5. This one's always negative. 7.5 here, that's going to be negative. 7.5 minus 7 is going to be positive. And then I can go back to a large number, 1,000. Positive, positive. And then I just do the results of this multiplication. I've got a negative, negative, negative. This interval is always going to be negative. In this interval, it's always going to be positive. In this interval, it's always going to be negative. Okay? And now I just have to ask myself, what are they asking? This was going to be basically less than 0 once we finish this up. This is less than 0, that's less than 0. Okay? So I have my rational function. When is this less than 0? Negative infinity to 7, union 8 to infinity. How about if I had r of x less than or equal to 0? The 7 is a vertical asymptote. I would never include the 7. Oh, I'm sorry. So it's not there, but it's down here. Once I simplified, I would not include, I would include the 8 for here, but I would never include the 7. So for less than or equal to 0, I would do the negative infinity to 7 union 8 to infinity. Okay, so let me look for any other special ones. These are all the same. Get them over to one side. Let's look at this. These are all the very same things, so it's easy to go through for our analysis. But let's take a look. And some of these, you just have to kind of go through and look at the pieces, okay? I want to know when x squared over x to the 4th plus 1 is greater than or equal to 0. Okay, and I have to look at them piecewise, the top and the bottom, and see if I notice anything. X squared, that's that basic graph. the only place the top is going to, the only place this thing is going to be equal to 0, remember, is the top. Nothing in the bottom can make me equal 0. Makes it pretty small, but not 0. So I know this was just the x equal to 0. But what about positives? Greater than. Well, the top is always this. What about x to the 4th plus 1? It's this shape, always above, but now this is moved up. This is never negative, and it's never equal to 0, so I don't have a vertical asymptote to worry about. So if I wanted to know where this is greater than or equal to 0, this is always positive, and it only depends on this. That's always positive and equal to 0. So negative infinity to plus infinity. Where's x squared over x to the 4th plus 1 greater than 0? I could do the sign chart and work this out, but there's no need from these pieces. Everywhere is going to be greater than 0, but I can't include the equal to 0. So this is negative infinity to 0, union 0 to infinity. I want to pull out my 0 point. Where's this less than or equal to 0? The only point that is always positive, so it's never going to be less than 0, but that equal to 0 is at that, the 0 when this is 0. So at 0, this is 0 over 0 plus 1, 0 divided by 1 is 0. This only works because equal to 0. And then finally, when is this equal to 0? That, no solution. This is the null set, empty set. Nothing's in there, there's no solution. Okay, so let's move a little bit. Let's work one kind of application of this, and let's see if we can figure out. So the big thing is just going to be able to write a function and then just set what are they trying, the limits of the solution. Okay, so here it is giving you a word problem. Fumio is constructing a circular koi pond in his backyard. What range of values may he have for the diameter of the pond if the area is to be no more than 78.5 square feet? Okay, so a lot of word problems come back to be geometry type problems. I've got some geometry in there, and those are very practical. I mean, you know, if I'm doing laying carpet, if I'm finding out how much area I need to paint a room. So in this case, we've got a circle. Let me see if I can get a good circle going. So they're saying, here's the area. I've got a circular pond. I need for this area to be no more than, so it's up to 78.5 square feet. No more than is anything less is okay, but once I can't get it past that 78.5. That's the inequality. Okay, so we have to work on our inequalities as we go. Okay, so how do we set this? What's the fundamental area of a circle? Area of a circle. The fundamental one is A is equal to pi r squared. Okay. Now, they are given what is the diameter. We can do this a couple of ways. We can solve for r. What's the limit on r? And then recognize that the diameter is twice r, or d over 2 is looking at r. Okay? So I could put this into there and solve, or later come back, now that I've got r, I can find the diameter. So it limits the radius. And then, so here is a picture. So if here, from the middle to any place, the circle is all the same thing. That's the radius to there. I want to draw this one. This is R. The diameter is the distance from the outside to the outside. So that's the radius from the center to the outside, plus the radius here, that's the 2R. Okay. So we're going to use, let's go ahead and use this version and then back off from the R to give me this, what my diameter is. So I need pi r squared less than or equal to 78.5. Okay. So let's do pi r squared minus 78.5. I need that to be less than or equal to 0. So let's use the same pattern that we've got here. Okay, we could do it a little quicker by saying here's the equal, take the square root, and then go, that has to be less than that. But let's kind of do it from here. And then I find my critical point. Where's that equal to 0? And then we're kind of right back over here, right? So I can do this as the difference of two squares, factor them out and get the 0. Or basically, we're back to here saying, when is this equal to 78.5? And then take the square root. They said use 3.14. So if I do this on my calculator real quick, that number I get plus or minus 5. Okay. So which one? Does the radius ever -5? No. Exclude. This is just practical. R equals to -5. Okay. So now we need for this to be less than or equal to 0. So that's a critical point 5. Do I need 5 bigger? If I put something bigger, 10, I would get that bigger than that. So I want this to be less than 5. So I need R to be less than or equal to 5. I want it in terms of the diameter. So I need 2R. If I multiply both sides by positive numbers, I don't have to switch. 2R less than or equal to 10. And this is the diameter. Okay. So this would be in feet. Okay, so if I do this as a check, 3.14 times my 5 squared times 25, I get 78.5. And then anything smaller would be less than that. Okay, so we'll work some more problems in lab like that, but let's call let's call a stop right here.